everybody. Today I will be talking to y'all about topic 27.6, which is titled The Limits of Resolution, the Rayleigh Criterion. So hopefully you've already watched the lessons on diffraction because this kind of expands on those. So this is specifically about diffraction through a circular aperture. So this first picture right here shows light pass through a circular aperture. You can see that there's a diffraction pattern that appears around that main bright spot. If you have two sources of light, so two distinct different objects, there's going to be a minimum distance that those two objects can be from each other and still appear as two distinct objects, not overlapping so much that you can't distinguish them from each other. This third picture here, those two objects have become so close that you can't distinguish them as two different objects. It looks more like one oblong object. So the Rayleigh criterion describes that minimum distance, minimum distance between the objects in terms of the angle between the two, so that they are resolvable. So resolvable just means that we can distinguish them from each other. And that formula is theta, which is the angle between the objects, equals 1.22 times the wavelength. So remember that is your symbol for wavelength. And d is going to be the diameter of the lens or aperture. And theta is the angle measured in radians. If you recognize that formula, it's because you may have seen it when you learned about diffraction. So here's a diffraction pattern where you have one area of greatest intensity, and then the distance from that maximum to the first minimum is 1.22 times the wavelength over d. So it's that same formula. And the reason that is important, if you look over here at this second image, so you've got two objects, two sources of light, separated by this minimum angle. So I could actually really add min to this equation here. As they go through the circular aperture and they create a diffraction pattern, the maximum point for one diffraction pattern is going to line up with the minimum point for the other, and vice versa. And that's going to be the closest those two objects can be so that these two maximum intensity points are distinguishable from each other. Any closer, and they'll start to constructively interfere into one larger maximum. Another use or application of this formula is in the spreading of a beam, so either a beam of light or of some other electromagnetic radiation. This image from the text is a transmission tower for microwaves. So one way that you can minimize the spreading that will happen is to increase the diameter of this transmission tower, I suppose. And by increasing that diameter, which is why you see really, really big dishes on these sort of towers, is to minimize the spreading so you get more of a uniform beam, and you can transmit whatever sort of information you're trying to transmit. So let's go through an example. This is problem 68 from the text. So if an amateur astronomer wants to build a telescope with a diffraction limit that will allow him to see if there are people on the moons of Jupiter. So we're going to figure out what diameter mirror is needed to be able to see 1 meter of detail on a Jovian moon at a distance of lots of kilometers from Earth. And we're given the average wavelength. So we're trying to see this little tiny 1 meter wide object at this incredibly far distance from Earth. So first off, we need to figure out our angle that we're dealing with in this problem. So if I'm looking at an object that's 1 meter wide, we can use the equation, technically arc length, but we can approximate that as the width of this object, equals r times theta, where r is the distance. So we're essentially going to figure out, looking at this thing way out here, what is this super, super, super tiny angle, theta. So we have a 1 meter wide object, and we need to divide that by our distance of 7.5 times 10 to the 8th kilometers, but let's multiply that by 10 to the 3rd to get 10 to the 11th, so that both of these are in units of meters, so that we can figure out our angle theta. Sweet. And then our next step is to use that equation. Minimum angle is equal to 1.22 times wavelength over diameter. In this case, it's diameter of our mirror, where lambda is our average wavelength, 600 nanometers, so that's 10 to the negative 9th meters. So I already know that my theta min is 1 over 7.5 times 10 to the 11th. That equals 1.22 times 600 times 10 to the negative 9th over d. Rearrange that and solve for d and plug in those values, and we get that d is 549 kilometers. Which, if you saw, the title of this question was Unreasonable Results. Follow-up question is, what is unreasonable about this result? Well, it's saying that this mirror over here on the surface of Earth would have to be almost 550 kilometers across. That is obviously unreasonable. And following up with part C there, what assumptions are unreasonable? It's just, that's not a feasible size for a mirror. So all in all, just an unreasonable question. All right, thanks a lot.